Okay, so it is an honor for me to introduce Vincent Pilloni, who is going to give the second lecture on p-adic automorphic forms.
Okay, so thanks a lot for the invitation. So I just have two quick announcements. So the first one is that from 4 to 8 September, 2023, there is a conference for Laurent Clausel in Orsay. And so I think you should all come. And the other thing is that I wrote notes for this talk, and they are at the very bottom of my webpage. So yeah, you can, I hope it's useful. Okay, so now I will give this second lecture on p-adic automorphic forms. So George spoke about the integral theory, and now I want to speak about the characteristic zero theory. So the theory over QP, over rigid analytic varieties over QP. And in characteristic zero, there is really an advantage, is that we have access to a period map. So that is a map from the Shimoa variety to the flag variety. And so we can try to perform lots of constructions on the flag variety using geometric techniques or representation theory techniques, if you like, and then pull them back to the Shimoa variety. Okay, and so that's roughly the plan of the talk. So I first want to consider equivariant objects on the flag variety. Then I want to study their pullback to the Shimoa variety, and so that's geometric sense theory. Okay, and finally I want to give an application to the construction of overconvergent modular forms. Yeah, okay. But I do this only for GL2 because, I mean, we decided that we should stick to GL2, but lots of the things I'm going to tell are, I mean, they exist for very general Shimoa varieties. Okay. All right. So let's start with introducing some, well, maybe introducing this flag variety. So since we're doing modular curve, it's just P1. So the group G is GL2. So I take the upper triangular Borel. It has a unipotent radical. Yeah, and we take the maximal torus to be the diagonal torus. Okay, so all these have Lie algebras. So the Lie algebra of G, I denote by a Gothic G. The Lie algebra of B by a Gothic B. The Lie algebra of U by a Gothic U, and well, the Lie algebra of T, I will denote it by a Gothic H because I think it's what we usually do. Sorry. Okay. Then maybe I also like to use the space of characters of the torus, and maybe I like to label them like this. So a K and a W in this square, such that K is congruent to W mod 2. Yeah. And the rule is that K comma W acting on T1, on T inverse Z is T to the K, Z to the W. Okay? So somehow K is giving the action on the torus of the semi-simple group, SL2, and then W is the action on the center. All right. So now, okay. So now the flag variety is B mod G, okay, and it has a G action by right translation. Okay, and yeah, I should say that everything is viewed as adic spaces over space CP. Okay. So yeah, so we have the Weil group. So the Weil group is generated by two elements. Yeah. Okay. Yeah. Okay, and we have the Brouillard stratification. So the flag variety is B over B union BW0 B over B. Okay, and so this is A1 and this is infinity. Okay, and so that's the Brouillard stratification. Brouillard stratification into B orbits. Okay, and so it's indexed by the Weil group. Okay, all right. So okay, so now we'd like to study certain equivalent objects on the flag variety, and so let's first study G equivalent objects. Yeah. So let's consider this category co-G FL, and so its objects are: you have F, a covariant sheaf on the flag variety, and it's equipped with a G semilinear action. Okay, so well, let's be precise about the meaning of this G semilinear action. So we have two maps from G to the flag variety. Yeah, so we have the action map that we call M, and then we have the second projection map that we call P. Okay, and so this semilinear action is really an isomorphism between the pullback via M of F and the pullback via P of F, which satisfies some, say, cocycle condition, which makes sure that the action is associative. Okay, right. So that's a category. That's an abelian category, and actually it's very easy to describe. So I'm going to describe it now. So let's denote by rugby the category of finite dimensional representations of B on CP modules. Okay, and so we have two functors. So if we have a G equivalent sheaf on the flag variety, what we can do is take the fiber at infinity. And so that way we get a representation of B, okay? Okay, because B is the stabilizer of infinity, okay? But we have a functor in the other direction. Okay, and so what can you do? If you have a pair V rho, you can build a G equivalent sheaf like this. So you take the pullback. So sorry, you take some tensor product of pi lower star of OG. So pi is the orbit map of infinity. So it's this map G FL G maps to infinity G. Okay. So you take the pi lower star of OG tensor V, then you take the invariance for the left tensor rho action of B. So this is B action, and this still has a right G action. Okay. Yeah. So in other words, I'm using that this is a B torsor, right, with action of B on the left. And it's also G equivalent B torsor with G action on the right. Okay, and so this is what I'm using to define this. Okay, and so these are equivalencies. Okay, are quasi-inverse. Are quasi-inverse equivalencies. Okay, so now we can use this functor to describe a number of sheaves. Okay, so let me give a list of examples. So the first thing we can do is consider the rank 1 objects. So if we take a character of the torus, okay, so in particular it's a representation of B, and so we can define O kappa FL to be the functor F. Well, not really attached to kappa, but I want to attach it to W not kappa, okay? And the reason for doing this is that if kappa is k comma W, is k comma W, actually this O kappa FL with this normalization is really going to be O of k over FL, right? So it's the degree k invertible sheaf with certain equivariant structure, okay? Okay. So now there's a second thing you can try to check as an exercise, is that if actually V is a G representation, okay, which restricts to a B representation, then actually f of V is trivial. Okay, so this is OFL tensor V, okay? And so in particular, we can apply this to the standard representation. So the standard representation of G, well, as a B representation, it has a filtration. So you have the sub, where you're acting by the character 1, and then you have the quotient where you're acting by the character -1. Yeah, so if you apply F, you get the tautological exact sequence over the flag variety. Okay. All right. Okay. And maybe yeah, it's very possible that at some point I will stop writing O kappa and just write O of k, and there will be a W somewhere, like the action of the center, but I will forget it. Okay. So this is just O of -1, and this is just O of 1. Okay. So now there's another example we may want to look at. So we can consider the Lie algebra equipped with its adjoint representation. Okay, and so the Lie algebra, it has a filtration. So you have the Lie algebra of B and then the Lie algebra of U. And so you can apply the functor F to all of these guys. And so you get F of G, which by what we've just said, since G is a G representation, is a big G representation, this is just the trivial bundle. So OFL tensor G. Okay, and well, in the theory, this guy has another name. So sometimes it's called G0 not, like this. Okay, so I may use this notation also. Then you have F of B. Okay, and so F of B also in the theory, it's often called B not. Okay, and this B not has a very concrete description also. It's the sub bundle of this trivial bundle of the moving Borel. Okay, so in other words, if I pick a point X in the flag variety, then the stalk of B naught at X is X -1 BX inside G, which is G naught at X. Okay, so this is the universal Borel Lie algebra. Okay, and then similarly you have F of U, which is also denoted by U naught in the theory. So now each of these graded pieces in this filtration, they have also some interpretation that I want to recall. So yeah, maybe I go there. So yeah. So what is, sorry? Yes. Oh, well, I mean, this is CP, but with action of the Borel by the character 1, 1, okay? So CP 1, 1, this is CP plus B action via 1, 1. Okay? No, no, this is not the Steinberg, this is the standard. Sorry? Yeah, it's a short exact sequence. Like this is the standard. So ST is this is CP square. Okay. And that's maybe the first basis vector. And that's the second basis vector. Yeah. This projection to the second basis vector. Yeah. Okay. So so let me give the interpretation of each of the Greux there. So you have a map from G to the tangent sheaf, okay, which is very concretely given by. So if you take some elements, so there will be matrag G and small g's, and so if you have some G there, then and if you have a function, then you can attach to it the function x goes to d over dt f of x exponential tg. Yeah. Okay, and so that's sorry, maybe f goes to this guy. Okay. Yeah, but I said I switched. Sorry, I mean. Yeah, I said when I use the functor f, I use the. Yeah, okay, yeah. I think it makes sense. I mean, or I could change the definition of f by putting a dual somewhere or whatever. Yeah. Okay, so I mean, so yeah, like you see, so since G is acting on the flag variety, then the Lie algebra is acting by derivation, and here's the formula. Okay, and so actually you can extend this linearly into a map from G naught to TFL, and then actually there's an easy proposition is that this map factor through B naught, and so you get an isomorphism between G naught mod B naught and the tangent space. Okay, actually you could also prove this abstractly because this TFL is G equivariant, and so you could just look at the fiber at infinity, and that's G over B, and yeah, okay, but that's okay. So this is the tangent sheaf. So now let's come to the next graded pieces. So we have B naught mod U naught. So B naught mod U naught, this is f of h, okay? Because yes, but now this has trivial B action, okay? And so therefore, since this has trivial B action, f of h will just be OFL tensor H. Okay, so this is the trivial sheaf. I mean, this is a trivial bundle with global sections H. Okay, and so we get some, map from H into B naught mod U naught. Okay, and this H is called the horizontal carton. Okay, so maybe you can denote it H or, and so in the sense that, well, inside J naught mod U naught, you have two cartons. You have the fixed carton, the one that's not moving with the point, and then you have this one which is actually moving with the point on the flag variety. So it's, I mean, it's just the carton inside the moving the universal Borel, okay, or Borel mod unipotent, okay. Yeah, Okay, and then U naught is just the dual of TFL, and so this is just omega 1 FL. Okay, so these were some examples. Okay, so now let's move and consider matrag G equivalent. Is the yeah. This is the moving one. Yeah. Huh? No. This, I mean, this one is right. I mean, you have, yeah. I mean, you have like, okay. Well, let me clarify this. Like inside G naught mod U naught. No, U naught. You have G. Okay. Like that's well, I mean, you have G. Yeah, goes to G naught. Yeah, and so you have a G which is not moving inside G naught mod U naught, and inside this G you have an H which goes to G naught mod U naught. Okay, and that's the not moving carton. Okay, so that's not the horizontal one. But then you also have inside G naught mod B naught you have mod U naught, you have B naught mod U naught, and inside this one you have another carton which is the moving one. Okay, and the two they only coincide. Maybe at the point at infinity. Okay. Yes. You can. Sorry. Oh. I mean. Sorry. Well, yeah. Okay. Yeah. Okay. All right. Okay. So now let's move to G equivariant sheaves. Okay. So we have an other category which we now only look for equivariant sheaves for the Lie algebra. Okay. So its objects as F, which is coherent, and G is acting on F, okay, and it's acting by derivation. So it means that if I take small g, well, yeah, so I have matrag G's, okay. So if I take small g in matrag G, then, well, G of A F should be G of A times F plus A times G of F. This is for A F in OFL tensor F plus F, okay, and also there should be some compatibility with the bracket. So G prime is equal to G prime minus G prime G. Okay, so that's another category. And so what can we say? So I mean, yeah, so there's this important remark that so if you take such an F in that category, then actually so there is an action of G by CP linear endomorphisms, right? But so you can extend this action linearly to an action of G naught on the endomorphism sheaf of F, okay? But now you can restrict this action to B naught. And now, since B naught is acting trivially by derivation on the scalars, this becomes an action by linear endomorphism, okay? And so from this, we draw the following remarks that so B naught acts trivially on F. This really means that we do have an action of G naught mod B naught on F, but G naught mod B naught is just the tangent shift. And so this means that actually we have a connection on F. And so this means that F is a D module. Okay. So now what happens if only U naught acts trivially on F? Well, so if U naught acts trivially on F, then we do get an action of B naught mod U naught on F, okay? And so in particular, the horizontal carton is acting on F, okay? And well, I just say it in words, but if the horizontal carton acts by a scalar, then and maybe the scalar is lambda, then actually F is what's called the twisted D module for the parameter which corresponds to the scalar, okay? And of course, if it acts by 0, then it's just a D module. All right, so now what will be quite important for us is the cohomology of U naught. And so let me define this. So let's define the cohomology of U naught on F to be the following complex. Yeah, so this is this complex where objects are in degree 0 and 1. Okay. And so each of the cohomology sheaves, they belong again to the same category. Yeah. Okay, and so there's like a good subcategory of co-GFL. And so this is the category of objects which are killed by U0. Yeah. So if you want, yeah, these are some kind of universal twisted D modules or whatever. Okay. So now well, yeah, I mean, yeah, so yeah, so I guess, yeah, so maybe D modules are equivalent to certain UG modules by taking global sections, because the like yeah, so yeah, so there's some there's some Beilinson-Bernstein equivalents there that you can formulate. Yes, just for the guys which are maybe killed by U0, and then you impose the action of the horizontal carton, and then you can take the cohomology, and well, yeah, there are some equivalencies between certain categories of UG modules with a specified central character. Yeah, but we won't need this. Yeah. Yeah. Yeah, well, yeah, it's true. It's true that there. Okay, so actually, I'm giving a simplified version of the theory, and if we want it to be serious, we should consider also infinite rank sheaves, but we're also doing adic spaces, and so we would need to consider quasi-coherent sheaves on adic spaces, and that's a complicated theory because, well, because maybe you have to use the solid formalism. And well, I don't. Yeah. So I decided not to. I mean, I decided to give this mini version, but you should keep in mind that there's a better version of this with infinite dimensional sheaves. And actually, at some point, I'll cheat a bit. So like I'll state some results for these finite dimensional sheaves, which I can state easily. But then I will pretend that some generalization exists for infinite rank sheaves. Yeah. So that's, yeah, so that's for pedagogical purpose. Yeah. No, I mean, so far you can, I mean, no, but so far we are just making definitions, right? So well, I mean, this is just, I mean, you have a map. Like what's clear from here is that you do have a map like this, right? Yeah, because this action and then you extend it. Yeah. And so you do have this map, and then you can just move the U0 to the other side because it's locally free. Yeah. Okay. So yeah, so maybe, yeah. I should also say that, yeah, I mean, we also like to consider this category where you are both matfrag G and G equivalent. So you are equivalent for the two guys. Yes, and so the objects are just F, which are simultaneously G equivalent and G equivalent. Yeah, and you impose some weak compatibility between the two equivalent actions. Namely, you impose that this map, G tensor F to F, is also big G equivalent. Okay. All right. So that's, I mean, yeah, I think we'll be interested in this category also. Okay. So let me also remark that if we just consider G equivalent shift, so big G equivalent shift, we can differentiate the G action. And so we get, and so you can go to this co G comma G FL, and then you can also just forget the big G action, and so you go there. Okay, and so this is by differentiating the big G action. Okay, so let me maybe just give some examples of this. So in particular, I mean, so we had these rank 1 guys, O kappa FL, and so I claim that they indeed belong to the category of objects which are killed by U0, and that the horizontal carton acts by omega not kappa. Okay, so you can try to check this as an exercise, but let me just give some hint. Is that so we've seen that co-GFL, this is the same thing as rub B by going to infinity, and so the U naught action, if you go to infinity, it just becomes the U action, and the H horizontal action, if you go to infinity, it just becomes the H action. Okay, and so if you can establish this, then you're good. All right. So so I think so I think now I'm done with sheaves over the full flag variety. Yeah. Yeah. Okay. So it's true that also you can prove that this category co-GG, this is the category of G comma B modules. Okay. Yeah. Okay. All right. And again, this is the finite dimensional version of something that also exists. Yeah, in more infinite. The dimensional version. Okay. So now, so now, I mean, if you remember from, so right now we are doing some preparation on the flag variety, and so if you remember from George's talk, so he spent some time trying to construct p-adic families of modular forms. So modular forms, they have some weight, okay, which is an integer, or if you want a character of our torus. But then he wanted to consider p-adic weights, okay. And so here we're going to do exactly the same thing. Now, remember that George, when he did this thing, he had to restrict to a certain nice locus of the Shimura variety, which was called like the ordinary locus or the Guza variety. And so there's a similar story on the flag variety where now we're going to restrict on Brouhaha strata. Okay? And so on Brouhaha strata, things, I mean, like you have a bit more freedom. So, yeah, so now I want to consider GB equivalent sheaves on Brouhaha strata. Okay. So, so the proposition is the following. Okay. So what I'm interested in is to interpolate these rank 1 objects. So obviously over the full flag variety, it's impossible because they have, I mean, there's this degree, and the degree is a discrete invariant. It's in Z, and there's nothing to do. But of course, when you restrict, then you have more freedom. And so now, instead of starting with a character, an algebraic character, I'm going to start with, if you want, a character of the Lie algebra. So, or, I mean, so it's a character of H, or that's, yeah. Okay. Right, so now I really have a two-dimensional affine space of characters. Okay, and so I pick such a kappa, and now I claim that there exists a sheaf, so an invertible, object, O kappa A1 in this category co GB A1, okay, and an invertible object O kappa infinity in this category co GB. So I will put infinity there, but I will tell you in a second what this means. Okay. And okay, so what are the, so maybe I should say that this category co GB infinity, this is just the category of GB equivalent modules of finite type over the local ring at infinity. Okay, so that's the definition. Okay, so on the local ring at infinity, you still have an action of G, of B, and so you can look at finite type modules equipped with a semilinear action, and yeah, and that makes sense. Okay, so we have these objects. So the second thing is that they are, well, they are unique. Well, yeah, they are the only rank 1 object up to twist of the B action by a character. Okay. And if kappa is actually algebraic, then certain twists of these sheaves will actually glue. So if you take O kappa infinity, and then you twist the B action by omega naught kappa, and if you take O kappa A1, and then you twist the action by kappa, they glue to our previous sheaves O kappa FL. Okay, so these two things are twist of the B action. Yeah. All right. So yeah. So I think that's the picture. So let me quickly give an idea of the proof of this. Okay. So remember that these O kappa FL, so these invertible sheaves, they were constructed out of this B torsor. Okay. or maybe even out of this T torsor. Okay, we took some push forward and some invariance. So now we're restricting to let's do the thing over A1. So we're restricting to A1. So we have B node BW0 node B over B. But this I can rewrite it in a slightly different way. So I can rewrite it as B at W0 U0 over B at, okay, where B at and G at and etc. will be the formal completions. Formal completions of B, G at the identity. Okay? But now that I've written this cell in this form, I can produce a new torsor. Namely, I can look at B at W0 U over U at. Okay? Okay, and so that was the original guy was a T torsor. But this new guy, this is a T at torsor. Okay? Okay, so what else? What kind of action do I have also? I have a G action, so an action of the Lie algebra by translation. Okay, everywhere, that's fine. And I also have an adjunct action of B. Okay, so B still acts by the adjunct action because it normalizes U and B. Okay. Okay, and just as a side remark, this adjunct action is not compatible with the translation action by G that we had on that side. And this is kind of related to this twist when you want to glue, but okay, that's a technical detail. And so now what I can, so let me call this pi at, and maybe this was some version of pi. And so what I can do now is consider pi at lower star of the structural sheaf of this formal scheme. Yeah, but now I take the advantage that I have an action of T at and not only of T, and therefore it makes sense to take the locus, I mean, the subsheaf where T at acts by that character omega 0 kappa. Okay, and one can check that this is indeed an invertible sheaf, and that's what we call O kappa A1. Okay, so that's this idea that on Brouwer strata somehow you have a bit more structure. Yeah, and so you can perform such constructions. Okay, and well, and I guess the construction over infinity is a bit of the same flavor. So you can try to do this as an exercise. Or no. I mean that's the proof of one. Okay, yeah, that's the proof of one, which is the most serious thing. And then I think that the rest is a bit bookkeeping. I mean, okay. All right. So now it's time to go to the Shimura variety. Yeah. Yeah. What this that's the definition. Yeah. I mean. So why are they invertible? Because this is a T at torsor. Okay, like the whole game is to be able to do a construction, but not for algebraic weights, but for really weights characters of the Lie algebra, or if it's the same thing, characters of this formal torus. Okay, and so for this we need to produce a T at torsor. Previously we had a T torsor, and so we need to produce a T at torsor, and this is not possible over the entire over the entire flag variety, but it's possible over the Brouwer strata. Yeah. All right. So now we want to. So we spend. Sorry. Yeah. The exponential. I mean, it's formal algebraic here. It's not. Yeah. Exponential. Cavalierian characteristic 0. Yeah. Okay. So now it's time to try to pull back things to the flag variety, to the Shimura variety. Sorry. Okay, so these were some preparations. So, and as I told you, I think the idea is to do as much as computations we can do on the flag variety because everything is so explicit, and then go to the Shimura variety. Okay, so now that's geometric sense theory. Yeah, and so as references, I should recommend Pan's paper on locally analytic vectors in the completed cohomology 1 and 2, and also the articles of Juan Esteban Rodriguez. So, for example, geometric sense theory on rigid analytic varieties. Okay, and so I'll try to give some introduction to these works. Okay, so first, what's the setup? So we do have so the modular curve. So this is the compact modular curve of level KP. Okay, so we have E over X KP, which is the universal semi-abelian scheme, and we have omega E KP, which is the pullback. So that's the Hodge bundle. Like as in George talk. So this is the conormal sheaf of E. Okay. So now, well, so now we're going to pass to the limit over Kp, and so we let X Kp, so K upper P, to be the following object. So you take the inverse limit of the spaces over all Kp. Oh, sorry. Yeah. Okay. Sorry. So I have K, which is Kp inside G of the finite adders, which is G of Qp times the finite adders away from P. Yeah. But yeah, it's just some level structure, right? But it's okay. I mean, you can just think that maybe just think that K is gamma P to the n, like, okay. I mean, some level like this is very good. Okay, so just the principal level at P. Okay. So now we consider XKP. So we take this inverse limit of spaces, and then we give it some structural sheaf, which is the completion of the inductive limit of the sheaves that come from each finite level. Okay, and so the theorem is that this is a reasonable object. So the theorem of Peter, that this is a perfectoid space. Yeah. Okay, so now what? So now we have a diagram like this, which is like the most important diagram for us now. So you have some map from this perfectoid Shimura variety to the flag variety, and then you have the maps to finite level. Okay. So let me first say how this map is defined. So the period state map is defined by this universal property that the pullback of the tautological sequence over the flag variety is the Hodge state exact sequence. Yes, and where the middle guy, so this is some fundamental exact sequence in the p-adic homology of elliptic curves and abelian varieties more generally. And this TP of E, well, because we're on XKP, it carries a trivialization. And so this is just ZP square tensor OXKP. Okay. All right, so that's the period state period map. So that's this other one is the map pi KP. So this map is a KP torsor in the Pro et al. Topology. Yes, and this map period state is GQP equivalent. Okay, so on the flag variety you have an action of G, and so in particular you have an action of GQP. And this map, I mean, is essentially by looking at this, at this equality, this identity, then you deduce that this map is GQP equivalent. Okay, so here are some further properties of this map. So the map period state is affine, okay, which means the following, that if we let x, y be the coordinates on the flag variety, then period state -1 of the locus, so the standard open x over y is less than 1, is affinoid. And the same thing for the other standard open, of course. I mean, everything is GQP equivalent. Okay, so this is a bit like saying that, well, you see so here you have on flag variety, you have the sheaf O of 1, which is ample. At each finite level, you have the sheaf omega, which is ample. And this is a bit like saying that the pullback of omega on top, which is the pullback of O of 1, is still ample in a certain sense. Okay. But it's not a proof, right? I mean, it's something you have to prove. Okay, so one other thing is that you can look at the ordinary points of XKP, and you can look at the period state of these ordinary points, and this is inside the rational point. Okay, so why is this true? Because if you take an ordinary point, so you have the Tate module of the elliptic curve, but the Tate module itself carries a filtration, because you have the, so we saw this in George's talk. Okay, and so this filtration is defined on the Tate module itself, and therefore it's QP rational. Okay, and so this proves this, but you can actually prove some converse statement, namely that the period state -1 of flag QP, this is exactly the ordinary locus. I mean, up to some higher wrong points. Okay, and now the last thing I want to say about this map is that, so you have this sheaf OXKP, so the structural sheaf, and it makes sense to consider inside the sheaf of smooth vectors, which is the colimit over KP of the H0 KP OXKP. Okay, right? So this makes sense because, well, OXKP is GQP equivalent, and if you take any section over any open, then this open will be stable by a small compact open subgroup, and therefore you can speak of it being invariant, okay, because you do have an action. Okay, and but actually this sheaf is described, and so this OXKP smooth, this is the colimit of the PKP inverse of the sheaves of functions at finite level. So in other words, any smooth function comes from finite level, okay? All right. So now our goal is to pass from the flag variety side to the Shimura, to the finite level Shimura variety side. And so we need to write a functor. So let's write a functor. So on the flag variety side, we have these G equivariant sheaves, okay? And we want to transfer them to sheaves on the other side. So we want to go to sheaves over some finite level, but maybe not specified modular curve. So it means that we want to get a sheaf of OXKP smooth module. Okay, so what's the obvious functor to write? So you take some G equivalent sheaf there, okay? Then you pull it back to XKP, okay? And now you want to descend, so you need to take smooth vectors. Okay, so what does this mean? It means that you consider F tensored over the flag variety with OXKP. Yes, so that's the pullback via pH state. And then you take smooth vectors, so it means that you take the colimit of the cohomology of Kp, so as Kp goes to 1, acting on this, right? And so there, what I need to tell you is that the G action, so the Lie algebra action on F integrates to a Kp action for Kp small enough. Okay, so this is, yeah, I mean, this is something you have to check, but it's not very hard. Yeah, and so therefore this formula makes sense for Kp small enough, where Kp is acting diagonally, okay? And so that's a reasonable functor that allows you to pass from one side to the other. Okay, so of course, if you have more structure, it's better. So if your sheaf, the sheaf you started with was G, G equivariant, then actually you are going to get a GQP equivariant sheaf of OXKP smooth modules. Okay, that because just you're using the matfrag G action to take the smooth vectors, but then you still have the G action, and therefore it induces a GQP action on this formula. Okay, and so yeah, maybe let me give a name to this functor, and so let me call it VB in the sense that it's the vector bundle attached to an equivariant object on the flag variety. Well, I've not yet proved it's a vector bundle, but it will be the case. All right, so now it's, well, so we've written a functor. So we have some formula. So now can we compute this functor to some sense? I mean, and so the computation is actually the following. Okay. So first, I mean, first one should consider the category of guys which are killed by U0. Okay. And so if you take this category of sheaves which are killed by U0, then the functor behaves extremely well, in the sense that if you take your sheaf in this category, then VB of F is a finite projective over OXKP smooth. Yeah, and it has the same rank as the original one in the sense that you have the following formula. Yeah. So yeah. So somehow, yeah. I mean, you have this formula. So I don't know. I mean, if you're familiar maybe with Fontaine theory, you could think that maybe OXKP is some kind of period sheaf, and that maybe these are some admissible objects for which you have like a nice formula of this type. Okay, so that's a bit the idea. Okay. So now what happens if the sheaf is not killed by U0, then actually we do have the following formula. So actually you can derive the functor VB, and the derived functor of VB on F is actually the functor VB applied to the U0 cohomology of F, to the U0 cohomology on F, right? So the U0 cohomology produces sheaves which are in this category of objects which are killed by U0, and we do have such a formula. Okay. And again, there are some infinite rank versions of this, but they are a bit too complicated to state. I think so. I chose just to stick to this. Okay. So maybe let me just try to explain a bit this result. I mean, now, of course, I'm not going to prove it, but I can at least give some idea. Yes, sure. Sorry, yeah. Yeah, I don't know what are vertical bundles, but sorry. Vector bundle. Yeah, it's a vector bundle. I mean, it's finite projective. Okay. So yeah, so let me just try to explain somehow why we need to be killed by U0 for the theory to work well. I mean, somehow clearly the theory works well for the guys which are killed by U0, and maybe not so well otherwise. I mean, although you have a complete answer. So again, let's go back to this diagram. Yeah. Okay. So now, I mean, just imagine 1 second that this map, this pi KP map, this is a KP torsor, okay? But just imagine that KP were finite, okay? Then if KP were finite, we're just doing finite étale descent, and it's fine, right? Okay? But KP is profinite. Now, if this map were, so this map is profinite on the generic fiber, I mean, like as adic spaces over QP or CP, but if it were integrally profinite étale, okay, if it were integrally profinite étale, then we could still do descent, because we could reduce mod P and then, or mod P to the n, and then do some faithfully flat descent mod P to the n, and yeah, and pass to the limit. But clearly this map is not integrally étale because this guy is perfectoid. So it means that when we reduce mod P, we've been extracting lots of roots of P. Okay, so this map is ramified. Is very ramified. Okay. So the idea is that you can't. So the descent is not effective in general. Okay, and so the idea. I mean, yeah, I thank Juan also for discussing this the other day. Is that you kind of need to descend to some space which would be XKP mod U0, okay? Except that XKP mod U0 it's not so clear what it is, although I will try to give some meaning of it in some special situation. Yes, and that's kind of the condition that's given to you by your object being killed by U0. And then once you've descended there, then basically the idea is that the descent is effective. Okay, so but again, it's not very easy to give a meaning to this xkp mod u0. Okay, but it's still possible to give some meaning over certain fibers of the hot state period map, and so I just want to do this, and so I'm going to look at this diagram over the fiber at infinity. And so if I look at the same diagram over the fiber at infinity, then I have the period state -1 of infinity. Okay, and so this, so first, the reason I'm taking infinity is that at infinity, u0 is just u, and it is rational. Okay, like it comes from u, which is like defined over qp, if you like. And so what's this space? This space, this is the moduli of an ordinary elliptic curve with a basis of the Tate module. And the basis is such that the first vector goes to the multiplicative part of the Tate module. Okay? And on this space, you can define some sense a quotient by u0. Well, but instead of u0, you will just use the ZP point of u. And so you have this quotient, period state -1 of infinity divided by u of ZP. Okay? But that's a space that we actually saw in George Stokes, and that's the Igusa tower. So this is the Igusa tower. Okay? And so this is the moduli of E odd and an isomorphism of the multiplicative of ZP with the multiplicative part of the Tate module and with the étal part of the Tate module. Okay? And then you can get down to some finite level. Yeah. Okay? And so now what's going on is that this map, this is actually integrally pro-étal. Okay? This is what we saw in George Stokes. Okay? So along this map, the descent is effective. So this map has effective descent. Yeah. But this other map, it's extremely ramified. Okay? Because that's actually the perfection of the Igusa variety. Okay, there's some Frobenius on the Igusa variety, and that's the perfection of it. And so here you've really extracted all the roots. And so basically, if you want to descent objects, you somehow need to be able to descend on that side, but here you need to impose a very strong condition, namely that the UZP action is smooth, okay, which is like to say that the U0 action is trivial, and then you can descend. Okay, so I guess that's a bit the idea. Yeah, okay, I'm happy to discuss this after, but okay. Sorry, I mean it's a bit, well, I don't know. I tried something. Okay, so now, yeah, so now let's try to now. Yeah, I think it's time to apply this theorem and to give some consequences. Okay. Okay. So now, yeah, so we have the theorem which tells us which objects we can pull back and descend. And yeah, and so let's use this theorem. So maybe, so that's application example. Okay. So maybe the first application is we take this invertible sheaf over the full flag variety. Yeah, and so these guys, they are indeed killed by U0. Okay, so they are like the good guys. And so we can apply our functor to them. Yeah, and so we get something that we call omega kappa smooth over the flag variety. And actually this is, so what I claim is that there is really nothing new, namely this omega kappa, sorry, not over the flag variety, over xkp maybe. And so this, well, maybe not put anything. And so this omega kappa smooth is just the co-limit of the omega kp, where this omega kappa kp are the sheaves of modular forms on the finite level Shimura variety. Okay, so really, yeah, I mean, we did all this complicated construction, but here it's totally trivial. And here's the one-line justification. Well, let's do it in weight one. So by definition, period state upper star of O of one, this is omega one, maybe kp tensored OXK, OXKP. Okay, that's by definition. Okay, and so this formula is clearly this formula, and so it's witnessing this fact. That's for O of one, but you can get the other cases by twist, by tensoring. Okay, so what we can consider is the cohomology of this sheaf. Yeah, and so this is a GQP smooth representation which computes, and its H naught. Its H naught computes. I mean, its H naught is just the co-limit of the H naught x kp omega kappa kp. Okay, so this is just spaces of modular forms of all possible level at p. Okay. So maybe so in the notes you can see, if you like, that there's a connection between this result and Falting's extension, but I think I'm going to skip this, so I'm happy to discuss it after. I want to give maybe, sorry. Okay, I want to give two more applications, and since I only have 15 minutes, yeah, I perhaps skip this. But let me say that this theorem I stated it. I mean, a particular case of this theorem is the computation of the cohomology of Falting's extension. Okay, and it's actually used in the proof, that this computation of the cohomology of Falting's extension. So in other words, this theorem, it contains some non-trivial result about the p-adic Hodge theory of the modular curve. Okay. All right. So yeah. So let me give the second application to locally analytic vectors. Yeah. So this follows. This is the work of Pan. Okay. So if V is a QP, so let me fix some integer and denote by Gn. This is the subgroup of G, which is defined by Gn of R plus is 1 plus P to the n M2 of R plus. Okay, so this is the subgroup of elements which reduce to the identity mod P to the n. Okay, so this is some open neighborhood of the identity. So now assume that V is a QP Banach representation of Gn of QP. Okay. Okay. Then we have an orbit map from V to the continuous functions from Gn of QP to V, which is C0 Gn QP, maybe QP tensor V. Yeah. Okay. And actually, V identifies with the invariant vectors for the certain action of Gn of QP, and namely this action is maybe G prime acting on a function f of G is G prime f G prime minus 1G. Okay. Okay, all right. So now we can make a definition. And so we can define the analytic vectors inside V. So these are those vectors which have an analytic orbit map. Okay, and so the definition is that now you have to replace these continuous functions by the analytic functions. So you consider OGN, functions on GN, you tensor with V, complete, and then you take the invariance. Yeah? Okay, so that's the analytic vectors. Yeah, or maybe let me call them the N analytic vectors, okay, because I fixed N, but then I can also vary N. And so you can define VLA to be the colimit of the Vn N. Okay, and so that's a certain LB space, yes, which is the locally analytic vectors. So one advantage of the locally analytic vectors is that you can differentiate them. So the Lie algebra acts on VLA, and how does it act? Well, if you have an element G in the Lie algebra, what you can do, so you want, and so you have a vector V in VLA, so you want to define GV, and so how do you do this? You let act G on the orbit function of V, okay, but the orbit function of V, it's locally analytic, and so this makes sense, and then you evaluate again at 1. Yeah, okay, so that's the definition. Okay, all right. So now let's do this with the. So now we apply this to the locally analytic vectors in the in this structure sheaf. Okay, so we have that OX KP LA inside OX KP. Okay, so that's, I mean, this is some relative theory, but we can still make the same definition. So what is this? So what you have to do is to take the colimit over all KP of the H naught of KP acting on the germs of analytic functions at 1 on G, tensored with OX KP. Yeah, where OG1, this is the colimit of the OGN. Okay, so that's the germs of analytic functions at 1. Okay, so that's the yeah, I'm just translating this definition there. Okay, all right. So now the theorem. Okay, and so this is where I'm using some infinite version of this result here, is that actually this OXKP LA, this is the same functor VB, but applied to H naught U0 OG1 tensor OFL QP. Yeah. Yeah. Okay. And you have a formula like this, namely that OXKP LA tensored OXKP smooth OXKP. So let me call this sheaf CLA is this sheaf tensored OFL OXKP. Okay, so that's so that's like an infinite version of this. Yeah, sorry, that's the H naught U0 on this. Yeah. Yeah, because yeah. So okay, so yeah, so anyway, I think Louis will speak more about this. Okay, so I'm okay, but I would, okay, So clearly, I mean, I want to say that it's clear that this, I mean, when you write this formula, it's clear that this is VB of OG1 tensor QP OFL. I mean, that's a tautology. I mean, if you like unravel the definitions, okay. But then, and then this idea is that the functor VB, it always factors through taking the U0 cohomology. Okay. Okay. And so in particular, this, you can view this formula as also giving you some idea of the local structure of this sheaf, because it's very much like the local structure of this sheaf on the flag variety, which is rather explicit. I mean, it's written there, right? And it's totally explicit. Okay, but I will, okay. That's, Louis will take up on this. Okay. So don't worry. All right. And so I have 7 minutes to give my last application. And so this is now to the over convergent modular forms. Okay. So that's the last example. Okay. So now we will be on Brouwer strata. Okay. So so we're on Brouwer strata, and so on Brouwer strata we have, now we can take the character to be in this affine space. Okay. X star T tensor CP. And so we have two GB equivariant sheaves. Yeah. And they clearly belong. I mean, these sheaves, they are rank 1. So anything that's rank 1 is killed by U0. Okay. And so I can apply the theorem over there, but over the Brouwer strata. And so I can apply VB. And so I get sheaves omega kappa smooth A1 and omega kappa infinity smooth. And so these are invertible sheaves. Yeah. And let me say that this also works in family. Yeah. So like you can vary kappa and then you get a family of such sheaves. Okay. And so these are invertible sheaves and they are BQP equivalent. Okay. And so now how do we get over convergent modular forms of varying weight? Well, we just take the cohomology of these sheaves in an appropriate sense. Okay. Yeah. I should say it's perhaps not the simplest definition of over convergent modular forms. Like there are simpler definition for GL2, but I think it's a nice definition in the sense that it matches well with Louis' theory, and it's, I mean, and also you understand quite well how to generalize it when you set up the things that way. Okay, but it will maybe not be totally clear that it's equivalent to some more old-fashioned definition. Okay, so what do we do next? We take cohomologies. Sorry? Yeah, but it's smooth already, right? So it's Yeah. Oh, so you mean I still have to take some invariants? I have, sorry, two? Yeah. You know, I have one. Yeah, but I will do the H1 theory also. I mean, what? No. Yeah, I mean, this is Eier-Coleman theory. This is like the Eier-Coleman theory. Yeah. So now I do two things. Okay, but very quick. So I can give the definition. So what can we do? So we can we can do the classical thing, which is that we take the cohomology over pi state minus 1 infinity of omega kappa smooth infinity. Yeah. Okay. So that's like related to classical over convergent modular forms. But the other thing we can do is take the cohomology with compact support over pi state minus 1 of A1 of omega kappa smooth over A1. Yeah. And that's related to Eier-Coleman theory. Yeah. Okay. So both spaces, they have BQP action. Yeah. And actually, this BQP action is locally analytic. Yeah. And the Lie algebra B acts by acts via minus omega 0 kappa there, and it acts via kappa there. So B acts via kappa there. Okay. All right. So yeah, so these are some kind of, okay. So I think, yeah, one important thing I should say, and that comes up, is that when you do these things of working over Brouillard strata, then you naturally need to introduce support conditions. Okay. And so here is some example of support conditions. Okay, and so that's a new aspect of the theory. Yeah. So and now I can maybe give you the definition. So these are still BQP modules, but I want to take invariance by BZP to get something which is more like the traditional space of over convergent modular forms, and I stop there. So now what I can do is that I can take a character nu of TZP. So that's a p-adic weight in the traditional sense. Yeah. And the logarithm of nu is what I call kappa. And this belongs to X star TCP. And now I can define maybe M dag nu, well, maybe M dag nu. And so what do? I take the Hodge state by Hodge state minus 1 infinity omega kappa smooth infinity, but then I twist by so I have to twist by omega 0 nu. Yeah, and then I take BZP invariance. Yeah, and so that's the space of over convergent modular forms of p-adic weight nu. Okay, and similarly you can define a space of Eier-Coleman theory, so some n dag nu, and so this is the same formula, but with the H1 with support, compact support, you have to twist by CP of nu, and then you take the BZP invariance. Okay, and so all these spaces, they have an action of the UP operator, which is the double class of the diagonal matrix 1p minus 1, and so this is UP. Okay, and yeah, so I think I'll stop here. Thanks.